Um, Notice the third row down, relative penetrating power. So this is essentially how deep into your skin something could go. So an alpha particle, I guess that sort of baseline is given a 1. These have to be relative numbers and kind of somewhat made up. For beta emission, it's 100, and then for the gamma emission, 10,000. So that can go through, basically through your skin. X-rays, we know, goes until it hits bone, until it hits certain particles. Those are not listed here, but yeah, so in terms of listing all of the different particles, my guess is positron and electron are similar because of the mass and size. Gamma's probably the worst. Y'all should check me on that. Like, someone can Google that. I'm sure there's a YouTube video, someone much more entertaining than me explaining it. Okay. Let's see. So again, to go through this type of figuring out what product was left after alpha emission, we figured out the atomic number and the mass number. The atomic number gave us the element symbol. Okay? Does that make sense? It's pretty straightforward, actually. Okay, so beta emission. Here we're going to give off a beta particle, which is a high-speed electron. So again, the symbol for electron, E with a -1 atomic number and 0 for the mass number. In beta emission, we have high-speed electrons emitted by an unstable nucleus. And in fact, we're going to end up with the atomic number of the species on the product side is 1 greater than that on the reactant side. And what that means is that we create a proton. And so there is a process by which a neutron is converted to a proton. I believe I have an example of that, but later on, so we'll get to that. So carbon-14, atomic number 6, decays by beta emission. That's not something you should, at this point, be able to know. It's not something you're required to know, but there are ways that I will show you how to make educated guesses on how radioactive decay might occur. So if we're told that carbon-14 decays by beta emission, we know that it has to emit an electron. And so, again, what's our daughter nuclide? Yeah, I heard a nitrogen, and that's because we know that the atomic number has to be 7, right? 7 minus 1, 7 minus 1 gives us 6. So now we're balanced there. And in terms of the mass number, it's going to be the same as it is on the reactant side. Everyone okay with that? Okay. Mm-hmm. So for carbon dating, I think we have a slide on this. I believe they use a ratio of, so rusty right now. It's carbon-14. Yeah, it's carbon-14. Yes, because here it is. We will talk about it. The half-life of carbon-14 is 5,700 years. And so you can use that to figure out how long something's been around. Other questions? Okay. Gamma radiation. We represented gamma radiation with this symbol. This one's easy to figure out when we're looking at what products can be formed. Here we're just going to emit a gamma photon from an excited nucleus. There's This is often used, gamma radiation is often used in medical imaging. We are basically going to take an unstable nucleus and see how it decays through gamma radiation. And you may have heard of technetium-99. Anyone ever had to do any medical imaging or has been involved with that in some way? Yeah. So do you know, were you told the process, Naomi? No. Hit the button. Okay. So basically, in this type of imaging, technetium-99 is attached to a drug. It takes it to the desired location in the body somehow. I don't know, that's biology. And then you can image that location in the body because it's going to give off gamma radiation. And so the technetium-99 is what we call metastable. And we give that the symbol M. Technetium has atomic number 43. And when metastable technetium decays by gamma radiation, we get the stable form, which has the same mass number and atomic number, but it is energetically more stable. So not that exciting really of a reaction, but it does do a really cool thing where it gives off high speed, high energy radiation. Okay. Questions on that? Don't ask about the biology. Watch it. Okay, so then positron emission. Positron is like an electron, only positive. Again, we saw the beta plus symbol, but we can also use our symbol for an electron, but now we have a +1 atomic number. Okay, so these are equivalent symbols. Okay. Again, same mass as an electron, just a positive charge. Technetium-95 decays this way through positron emission. So we know it'll form our positron. And so in order to balance this equation, we're going to have atomic number 42, mass number 95, and that gives us symbol molybdenum. I think these reactions are fun. I could add 1 and 2 all day. It's good. Don't even have to write phases. Come on, what's not to love? Okay. We're almost through all of these, okay? Electron capture. This one's kind of neat. So here we have an unstable nucleus that is able to become more stable by picking up an electron from an inner orbital of all of the electrons that are available. Not a valence electron, those are the outermost ones. This picks up an electron from one of the inner shells. Excuse me. So here we have an electron then as a reactant as opposed to a product. So this is one of the few things where we have an electron, or 2 reactants, excuse me. So an example of this is potassium-40, atomic number 19. It's going to pick up an electron from an inner orbital to form, argon with atomic number 18. Again, 19 minus 1 to get 18. And then same mass number. Okay. Now, this is the example here where I have, what you end up seeing is that a proton is converted to a neutron. And while most of that's mostly physics, like the underlying process that this is going through is a lot of physics beyond what you need to know. Well, we can show this though through our nuclide symbols. So for a proton, it's going to have an atomic number of 1. We could use H. I guess your book uses that. That's what I showed on the table. Proton plus an electron. And if we add up our atomic number and mass number, we'll end up with a 1 and a 0, and that means we have a neutron. Okay, so you can see by nuclide symbol how we can take a proton, combine it with an electron to produce a neutron. Questions on, yes?
Is the electron replaced by a more outer electron after it's taken?
Yeah, so if we have an electron that goes from an inner shell into the nucleus, will most likely be a cascade of electrons going from the valence down into the inner shell. Yeah, and then it's also possible to give off radiation in this case. This is the way that you can actually, well, do I want to get into this? There's an instrument that we have in the department, a few of them. I think we used to use them in Gen Chem, called X-ray fluorescence. And so we were basically able to detect X-rays emitted from a nucleus. And so with that, you shine a high energy electron onto an atom, collection of atoms, a sample, and an electron is ejected from the inner shell. Other electrons will then fill in, and a light is given off, and then we collect that light. And the energy of that light is a signature for that particular atom because it's dependent on the energies of those orbitals. So there are ways to capture, to use these types of radiation for identifying heavy metals, for instance, in soil. X-ray fluorescence is often used in recycling centers as well, or junkyards. They have these hugely expensive pieces of equipment, but you can basically, they look like an X-ray gun. You zap it on a piece of metal, and it'll tell you what metals are in that sample. It's pretty cool.
Could you theoretically turn like chlorine into argon if you shot a positron energy?
Could you turn chlorine into argon if you shot a positron on it? I am not good at knowing what is possible in nuclear chemistry. I know very little about it. I mean, mathematically, that makes sense, but that's only simple math, not based on science. I don't know what the limitations are. Okay, other things, other crazy things that I won't know the answer to. That's not crazy, I'm just kidding. Okay, so spontaneous fission. Here we're going to take an unstable nucleus and we're going to see how it decays. And so basically what's going to happen is a heavier nucleus is going to split into lighter nuclei and release energy in some form. It may be radiation, it may be the form of a neutron, something like this, okay? So a good example is uranium-236. It undergoes spontaneous fission to form yttrium-39, iodine-136. So this is probably why we do iodide, because now you have it as a product of a spontaneous fission reaction. And what else? This is hard to see. So if we add these up, we have 96 plus 136. What does that give us? They can do that in their head and trust themselves. Gives us 232. And we have 39, and 53. So that's 92. Okay. So what could be some products? Neutrons, exactly. So the neutron is going to have a mass number of 1, atomic number of 0. We already balanced out our atomic numbers, right? So we have 92 if we sum these up, and that's what we have on the reactant side. So we have to have a 0 here. But we're short 4 in terms of our mass number. So if we have a neutron, if we put a 4 in front of it, stoichiometric relationship here, we will now be balanced on both sides of the equation. Questions on that? Now, knowing all of these parts, that's not something you're going to be expecting. But maybe something like that, recognizing that, okay? Okay. So let's take a look at a graph that will help us decide what types of radiation an isotope can undergo. So, in general, all nuclides with an atomic number greater than 83, so 84 and up, are radioactive. Okay. Does everyone get that song in their head when they say radioactive? Good. You're welcome. All right. Okay, so some nuclides are stable, carbon-12, carbon-13, they don't decay. But carbon-14 is an unstable nuclide. And so what we can do, and what people have done, is made a plot of the number of neutrons, and that's what's shown on our y-axis. This is number of neutrons, versus the number of protons, also known as the atomic number. Okay, this is neutrons, not mass number. So atomic number and number of neutrons. If there's a 1-to-1 relationship of protons to neutrons, that's shown by this red line. And that doesn't exist for most of the nuclides that there are, right? So what we have are all of these dots, the yellow dots and the blue dots, represent different nuclides. Okay, all of those are dots. And the blue line represents what we call the belt of stability. Okay. And so what we see is that those nuclei that are above the belt of stability, they typically decay by beta emission. Those that are below the belt of stability typically decay by electron capture or positron emission. Okay, something in the yellow below the blue dots. And then those that have atomic number of 84 or greater, we typically see alpha emission. Okay, so the heavier nuclides are going to decay by alpha emission. The lighter ones that are above this belt of stability, they're going to decay by beta emission. Those below, positron or electron capture. And so, thinking about what this means, as the number of protons and neutrons, as the number of protons increase, the number of neutrons in a stable nuclei needs to increase. And that's because the neutrons are needed to sort of keep the protons from interacting with each other in unstable ways. It decreases the repulsion reactions. Do I have any examples here? Okay, so rubidium 87. This graph's kind of hard to use, but we'll try. So 87, this is 85. Oh wait, 87, that's the atomic number. 85, 87 is somewhere in here. Okay. Oh, come on me. Oh, sorry. Start over, ignore all of that. Rubidium 87, okay, RB 87, and rubidium is 37, okay? So that's where I was getting confused. So atomic number 37, somewhere in here. And if we go up to 87, we are well above no, come on. Where am I making my mistake? Y'all see it? What's on Y? Number of neutrons. So how many neutrons in rubidium? Protons, 37. Yeah, 50. Okay, so we'll try this one last time. 37 and now 50. We're somewhere in here. Are we above that band of stability? We are pretty much above that band of stability. We're going to say yes, we are. This is hard to see on this graph. So it's going to decay by beta emission. Which means it's got to form an electron. And what's the other product? I'll do the easy one. This says 87. It's going to be 38 here in the bottom. So that's strontium. Okay. Well, I'll just tell you these others because the graph's not that great. Scandium 41. Scandium has atomic number of 21. So if we are looking at the graph, we're at 21 and 20. So I think that's below the belt of stability. Yes. This decays by electron capture or beta emission. Okay. And so that reaction is going to be this. So beta emission. Calcium. Okay. Questions on any of that? Okay. Yes. Which is the most dangerous? Gamma radiation's not great. What's that? I mean, so if this were dangerous, I think this is alpha emission. If this were dangerous, we wouldn't be able to have it. So that's probably not so bad. I don't know the others, but relatively speaking. If we go back to this one slide, let's see. Ta-da, we did basically all these slides. Radioactive decay chains. Let's do this and then we will pause it. So, there are some nuclei that will undergo one transformation, and still isn't stable. So uranium is a good example of this. And so basically what will happen is the nuclei will undergo a series of decays until eventually a stable element or stable isotope is formed. So uranium-238 is a good example of this. And we did the alpha radiation, alpha decay of uranium-238 as an example. It forms thorium, which, here we go. Each blue arrow represents alpha emission, so emission of that helium particle. The red is a beta emission, so an electron. Okay. And so once thorium can undergo beta emission to form, what's PA? Let's test my skills. PA, what's that element? Someone's gotta know. Okay, I'm glad actually. I'm glad we're all lost at this point. That's good. Okay, what is it? Protactinium. Commonly found protactinium. Which then undergoes another beta emission to form uranium, and then that undergoes another alpha emission, and eventually we get down to a lead isotope. Okay. In this plot, we have mass number and atomic number, so that's why it's sort of shown this way. When we undergo a beta emission, the mass number doesn't change, right? Because there's a 0 here in our mass number area. But the atomic number does change, and it increases because we're essentially forming that neutron. Okay, and then when we release our alpha particle, both the atomic number and mass number change. Okay, so decay chains. These I think that these show up a lot when we're doing like nuclear energy. There we go. Eventually you get down to something stable. Okay? Questions? Oh, yes.
Does it ever change states when it decays? Or,
What do you mean by change states?
like, I don't know if it goes to like radon.
Ah. Yeah, it could totally change. Right, so this is the reaction that forms radon. So that could be, that would probably be in the gas phase then. Yep, great question. Other things? All right, you all, have a great Thanksgiving. We'll all try to come back refreshed. And remember protactinium.